The next question is, choose the correct option having all the elements with D10 electronic configuration. So different elements are given and you have to find the elements which are all having the D10 configuration. So for this you have to know the general electronic configuration of the different groups present in D block. So let us start from group 12. Group 12 elements: zinc, cadmium, mercury. These elements are having the general electronic configuration N-1D10, in which their d orbital is fully filled, and Ns2. So this is the general configuration. Then if you go to group 11 elements, copper, silver, gold. For these elements also, their d orbital is fully filled, N-1D10, but their s orbital is having only one electron. So for group 12 and group 11 elements, they have D10 configuration. Then there is another one element also in group 10. Group 10 elements are nickel, palladium, platinum. In these elements, palladium alone is having the configuration 4D10 5s0 configuration. So in palladium also there is fully filled d orbital configuration. So with this information we will check the options. In option A, cobalt is given, cobalt, nickel, iron, chromium. None of these elements have D10 configuration, so option A is ruled out. Then the option B, copper, zinc, cadmium, silver. So copper is in group 11, zinc is in group 12, cadmium is also from group 12, and silver is from group 11. So all these elements have 3D10 configuration. So our correct option is option B. Let us check the other options also. In option C, palladium is given, that is having D10 configuration. Then nickel, iron, chromium and all is given. So the option C is ruled out. In option D also again nickel, chromium, iron is given. So option D is also ruled out. So the correct option is option B, in which all the elements are having 3D10 configuration. The next question is, identify the incorrect pair from the following. So the first option is photography AGBR. We already know in photography, silver bromide is used as it is a light sensitive salt. So it forms the image in the film when it is exposed to light. The next option is polythene preparation, that is polymerization of the alkene, and for this Ziegler-Natta catalyst is used. And we already saw Ziegler-Natta catalyst is titanium tetrachloride and triethyl aluminium. So both the option A and B are correct pair, but in question they are asking the incorrect pair. So let us go to this option C, Haber's process, that is synthesis of ammonia from N2 and H2. For this, the catalyst used is finely divided iron with some promoters like Al2O3 and K2O. So Haber's process, iron is used. This one is also a correct pair. Then going to the last one, Baker's process. Baker's process is the conversion of alkenes into aldehydes. And for this conversion, the catalyst used is palladium chloride and not platinum chloride. So in question, platinum chloride is given, so that is wrong. So the incorrect pair is option D. Let us go to the next question. Which of the following statements are correct? The M3 plus bar M2 plus reduction potential for iron is greater than manganese. The first statement is wrong because the standard electrode potential M3 plus bar M2 plus value for iron is plus 0.77 volt and for manganese is plus 1.57 volt. So from this clearly we can see that the standard reduction potential value of manganese is greater than iron. So from this what we can understand? Manganese is stable in +2 oxidation state due to the 3D5 configuration. 3D5 configuration is half-filled configuration. So to remove the third electron from this half-filled stable configuration, more energy is required. So it is having a greater reduction potential value. But in case of iron, Fe2 plus is having the configuration 3D6, but Fe3 plus is having the configuration 3D5. So after the removal of the third electron only, iron is having the half-filled 3D configuration. So it is easy to remove the third electron from this Fe2 plus. So it is having a low reduction potential value. So the first statement is wrong. Iron is having greater value than manganese is wrong. So let us go to the second statement. Let's go to the next statement. The higher oxidation states of first row D block elements get stabilized by oxide ion. So here first row D block elements means 3D series. So they are stabilized by the oxide ion. This statement is true because the oxide ion, that is the oxygen atom, we already know it is small in size and have high electronegativity. So due to this high electronegative nature, it strongly attracts the electron from the metal and forms strong sigma and pi bond. with the metal and it increases the stabilization energy. So the statement B is correct. Going to the third statement, aqueous solution of Cr2 plus can liberate hydrogen from dilute acid. This statement is also correct. So we already saw in key concepts itself, in 3D series, copper alone is having positive reduction potential value. So copper alone cannot liberate hydrogen from dilute acid, while all the other 3D elements can liberate hydrogen from dilute acid, and the Cr2 plus is having negative electrode potential value, so it can liberate hydrogen from dilute acid. Then going to the fourth statement, magnetic moment of V2 plus is observed between 4.4 to 5.2 bm. So for that you have to know the electronic configuration of vanadium. Vanadium is having the electronic configuration 3d3 4s2, and here V2 plus is given. So V2 plus is having the configuration 3d3. So here the number of unpaired electrons are 3. So the magnetic moment formula mu is equal to root of n into n plus 2. So in case of n you have to substitute 3 into 3 plus 2 is 5. So root 15, and the answer is 3.87 bm. So this range is between the values 3.4 to 4. Or you can write 4.0 bm, and the given range is 4.4 to 5.2, which is wrong. So the statement D is wrong, and the correct options are B and C only. So option A is correct. So the correct option is option A. The next question is, in chromium chloride, the number of d electrons present on chromium is same as in chromium chloride. Formula is CrO2Cl2. To know the number of d electrons, you have to know the oxidation state of chromium. So let us keep that as X. We know the oxidation state of oxygen is -2, and 2 oxygen atoms are there. So -2 into 2, -4. Then the oxidation state of 1 chlorine atom is -1. 2 atoms are there, so -2. And the whole compound is neutral, so everything equal to 0. X minus 6 equal to 0, X equal to +6. So the oxidation state of chromium is +6. Now we have to calculate the number of d electrons. The electronic configuration of chromium is core argon configuration 3d5 4s1. 6 valence electrons are there. Now chromium in +6 oxidation state, all the 6 electrons are lost, so it will be having 3d0 configuration. So the number of d electrons is 0. Now we have to check the options in which the number of d electron is 0. The first option is titanium in +3 oxidation state. Titanium is having the electronic configuration core argon configuration 3d2 4s2. Now 3 electrons are removed, so titanium 3 plus will be having the configuration 3d1. Then iron is having the electronic configuration core argon configuration 3d6 4s2. Iron in +3 oxidation state, 3 electrons are removed, so it will be having 3d5 configuration. Then vanadium is having the configuration core argon configuration 3d3 4s2. Now vanadium in +4 oxidation state is having the configuration, so 4 electrons are removed out of the 5 valence electrons, it will be having 3d1 configuration. So the first 3 options are not having 0 electrons in d orbital, so our answer is definitely the option D. So let us check that. Manganese is having the electronic configuration core argon configuration 3d5 4s2. So totally 7 valence electrons are there, and here manganese in +7 oxidation state is given. All the 7 electrons are lost, so 3d0 is the configuration. So this is same as Cr6 plus. It is also having 0 electrons in d orbital. So the correct option is option D. The next question is, the set of correct statements is manganese exhibits +7 oxidation state in its oxide. So we already saw that the higher oxidation states are stabilized by the oxide ion, and in case of manganese, it exhibits the oxidation state from +2 to +7, and the +7 oxidation state exhibits only in the oxide form and in the compound Mn2O7. We know that oxygen has the ability to form multiple bonds with the metal, so it is easier to stabilize the higher oxidation state. So the first statement is correct. Then going to the second statement, ruthenium and osmium exhibit +8 oxidation state in their oxides. So the second statement is also true. So they belong to group 8. The group 8 elements are iron, ruthenium, osmium. For iron, the maximum oxidation state it can exhibit, the highest oxidation state is +6 only. But for ruthenium and osmium, it can exhibit +8 oxidation state also. This is because iron is a 3D series element, ruthenium is a 4D series, and osmium is a 5D series element. So as we go down the group, the higher oxidation states are more stable. As we already saw, the 4D and 5D orbital are large and diffuse, so easily they lose the electron and they form stronger bonds. And also down the group, the effective nuclear charge increases, so they stabilize the higher oxidation states effectively. So the statement 2 is also correct. The next statement is scandium shows +4 oxidation state which is oxidizing in nature. This is wrong. Scandium is having the electronic configuration, core argon configuration 3d1 4s2. It is having only 3 valence electrons. So the only oxidation state exhibited by scandium is +3 oxidation state, and it is stable in +3 oxidation state. It does not exhibit +4 oxidation state itself. So the statement 3 is wrong. Going to the fourth statement, chromium shows oxidizing nature in +6 oxidation state. This statement is true. So it belongs to the group 6. The group 6 elements are chromium, molybdenum, tungsten. So all these elements exhibit +6 oxidation state, but the +6 oxidation state is stable only in case of molybdenum and tungsten. For chromium, the +6 oxidation state is unstable. So it easily accepts electron and itself it is reduced. So when the species is itself reduced, it can act as oxidizing agent. So it is having oxidizing nature. So the chromium shows +6 oxidation state, that is correct, and it is oxidizing in nature. Why? Because the +6 oxidation state in case of chromium is unstable. So it accepts electron and it is getting reduced. So it can act as an oxidizing agent. So the statement 1, 2 and 4 are correct. So the correct option is option B. So the correct option is option B. Statements 1, 2 and 4 are correct. The next question is, in following pairs, the one in which both transition metal ions are colorless is. For a transition metal ion to be colorless, the electronic configuration should be either completely empty D0 configuration or completely filled D10 configuration. So this should be the electronic configuration. In this case, the transition metal will not show any DD transition. There is no DD transition, and the transition metal ion will be colorless. So let us see the option. Scandium 3+. Scandium is having the configuration 3d3, 3d1, 4s2. So scandium in +3 oxidation state, all the 3 electrons are lost. So it is having 3d0 configuration. Then going to the next option, zinc. Zinc is having the configuration, core argon configuration 3d10, 4s2. So in Zn2+, the two 4s orbital electrons are lost. So it will be having 3d10 configuration. So as we saw, d0 and d10 configuration will have colorless metal ions. So the option A is correct. So let us check with the other options also. So in option B, Ti4+ is given. Titanium is having the configuration 3d2, 4s2. Then titanium in +4 oxidation state, all the 4 electrons are lost. So it is having 3d0 configuration. Then going to copper. Copper is having the configuration 3d10, 4s1. Then Cu2+ is having the configuration 1 electron from 4s orbital and 1 electron from 3d orbital is lost. So 3d9 configuration. So in 3d9 configuration, there is DD transition, so that metal ion will be colored. So option B is ruled out. Then in option C, titanium in +2 oxidation state is given. So only the 4s electrons are removed. So the 3d2 configuration will be there. So that pair is not correct. Then going to the next one, Mn2+ is given. So Mn2+ will be having the configuration 3d5. 3d5 will show DD transition. So the option D is also ruled out. So the correct answer is option A. Which of the following 3D metal ion will give the lowest enthalpy of hydration when dissolved in water? So the enthalpy of hydration depends on the charge density of the ion. So the enthalpy of hydration is directly proportional to the charge density, and we know the formula of charge density. Charge density is equal to charge divided by volume. So here the given ions are Cr2+, Mn2+, Fe2+, and CO2+. So as we go across the series, the atomic size decreases and the atomic volume also decreases. So here in this case, we can write the ionic volume decreases. But this Mn2+ ion is having 3d5 configuration. This stable configuration makes the orbital to be slightly expanded, and this Mn2+ will be having the largest volume. So among the given species, Mn2+ will be having the largest volume, and here charge density is inversely proportional to volume. So as Mn2+ is having largest volume, Mn2+ will be having the least charge density, or you can say the lowest charge density, and therefore it will be having the lowest enthalpy of hydration when it is dissolved in water. So the answer is B, Mn2 plus. Which of the following has least tendency to liberate H2 from mineral acids? So the given options are copper, nickel, manganese, zinc. In 3D series, copper is having the electrode potential value as plus 0.34 volt. It is having positive electrode potential value, so it cannot liberate H2 from mineral acids. And in reactivity series also, copper lies below hydrogen in the reactivity series, so it cannot displace hydrogen gas from the mineral acid. So the option A, copper, is correct. The next question is the spin only magnetic moment value of the compound with strongest oxidizing ability. So it is going to act as an oxidizing agent, so itself it should be reduced. So the given species are among MnF4, MnF3 and MnF2. So for this, first you have to know the number of d electrons present in the metal in each of the compound, and for knowing the number of d electrons, you have to calculate the oxidation state of the metal. In first compound MnF4, let us keep manganese as X. For one fluorine atom, the oxidation state is -1. 4 fluorine atoms are there, so X minus 4 equal to, the overall compound is neutral, so everything equal to 0, so X equal to plus 4. So the electronic configuration of manganese is core orgon configuration 3d5 4s2. Then manganese in plus 4 oxidation state. So 4 electrons are removed, 2 electrons from 4s orbital and 2 electrons from 3d orbital are removed. So it is having 3d3 configuration. Now let us see the next compound. The next compound is MnF3 X, and for one fluorine atom the oxidation state is -1. 3 atoms are there, so X minus 3 everything equal to 0, X equal to plus 3. So we already saw the electronic configuration of manganese 3d5 4s2 and the manganese in plus 3 oxidation state. 3 electrons are removed, 2 electrons from 4s orbital and 1 electron from 3d orbital, so it will become 3d4 configuration. Then going to the next compound MnF2 X, 2 fluorine atoms are there, so -2 everything equal to 0, X equal to plus 2. Manganese is having the configuration 3d5 4s2. Manganese in plus 2 oxidation state, it will be having 3d5 configuration. Now the given condition is it is a strongest oxidizing ability, it is having a strongest oxidizing ability. So I already told that it should itself be reduced. So what is meant by reduction? Reduction is gain of electrons. So out of the 3 configurations, which configuration will easily gain electron and it will become stable? So the 3d4 configuration will easily gain electron, and after the gain of electron, it will become 3d5 configuration, which is half-filled configuration and it is more stable. So the other 2 configurations do not easily gain electron because 3d5 configuration in case of Mn2 plus is already half-filled and it is more stable, and the 3d3 configuration in case of Mn plus 4 is T2G3 configuration. This is also half-filled energy level configuration, and this one is also already stable. So the strongest oxidizing ability is for the species Mn plus 3. Now what is the question they are asking? The spin only magnetic moment value. So spin only magnetic moment value is you have to find mu. So the formula of mu is root of n into n plus 2. So n is the number of unpaired electrons. So the number of unpaired electrons we have already calculated. It is having 3d4 configuration. So the number of unpaired electrons 1, 2, 3, 4. 4 unpaired electrons are there. So mu is equal to root of 4 into 4 plus 2 is 6. So root of 24. So the answer is 4.89. And here they are asking the nearest integer. So we can round off this value to 5. So the answer is 5 bm. So here in this question the answer is 5 bm. Among CO3 plus, Ti2 plus, V2 plus and Cr2 plus ions, one if used as a reagent cannot liberate H2 from dilute mineral acid solution. Its spin only magnetic moment in gaseous state is. So out of the given ions, CO3 plus is a strong oxidizing agent. A strong oxidizing agent easily accepts electron and is itself reduced. So to liberate H2 from dilute mineral acid, the species should act as a reducing agent. It should act as a strong reducing agent, but out of the given species, CO3 plus is a strong oxidizing agent and it is easily accepting electron. So this CO3 plus easily accepts one electron and it is converted to CO2 plus. So this CO3 plus cannot liberate H2 from dilute mineral acid. Now they are asking us to find the spin only magnetic moment in its gaseous state. So the species is CO3 plus. Cobalt is having the configuration 3d7 4s2, and cobalt in plus 3 oxidation state is having the configuration 3d6. So for this 3d6, how many unpaired electrons are there? 1, 2, 3, 4, 5, 6. So 4 unpaired electrons are there. So n equal to 4, and the spin only magnetic moment formula is root of n into n plus 2. So this we already saw in previous question. Root of 4 into 4 plus 2 is 6. So root of 24. So the answer is 4.87 bm, and round off to the next integer. So the answer is 5 bm. The next question is spin only magnetic moment value of M3 plus ion in gaseous state from the pairs Cr3 plus bar Cr2 plus, Mn3 plus bar Mn2 plus, Fe3 plus Fe2 plus, and CO3 plus CO2 plus that has negative standard electrode potential. So here the condition is negative standard electrode potential of the M3 plus bar M2 plus species. So in 3D series, up to chromium, the M3 plus bar M2 plus value up to chromium is negative, and after chromium the value will be positive. So if we compare this Cr2 plus electronic configuration with Cr3 plus, chromium in plus 2 oxidation state will be having the electronic configuration 3d4. Chromium in plus 3 oxidation state will be having 3d3 configuration, which is half filled T2G3 level configuration, and this configuration is more stable. So the Cr2 plus ion easily loses one electron and it is converted to Cr3 plus. So the electrode potential value will be more negative in case of chromium. And if we see for Fe3 plus bar Fe2 plus also, the configuration of Fe2 plus is 3d6. The configuration of Fe3 plus is 3d5. So Fe2 plus easily loses one electron and it will be converted to Fe3 plus. But in this case, the electrode potential value is not negative, but it is less positive. So here the value is positive, but not more positive, it is less positive, and the electrode potential value is plus 0.77 volt. So the less positive value indicates that Fe2 plus readily converts to Fe3 plus due to the stable half-filled configuration, and the more negative value represents that Cr2 plus readily converts into Cr3 plus due to the half-filled T2G3 energy level configuration. Now in this question they are asking the pair which is having negative electrode potential. So the pair that is having the negative electrode potential is chromium in plus 3 oxidation state and Cr2 plus. Now you have to find the spin only magnetic moment value of M3 plus ion. So chromium in plus 3 oxidation state is having 3 unpaired electrons. So the value of magnetic moment mu is equal to root of n into n plus 2. So which is equal to root of 3 into 3 plus 2 is 5. So root of 15. So the answer is 3.86 bm. And when we round off to the nearest integer, it will become 4 bm. So the answer is 4 bm. The next question is the electronic configuration of platinum is. So platinum belongs to group 10. In group 10, the elements present are nickel, palladium, platinum. So nickel is a 3D series element, palladium is 4D series, and platinum is 5D series. And for platinum, you are having fully filled 4f orbital also. So 4f14 is there. The electronic configuration of nickel is 3d8 4s2. The electronic configuration of palladium is 4d8 5s2. This is the expected configuration of palladium, but due to the increased nuclear charge, both the electrons from the 5s orbital are promoted to the 4d orbital. So the actual configuration of palladium is 4d10 5s0. So this is the actual configuration of palladium. Now coming to platinum, the expected configuration is 4f14 and the next orbital is 5d, 5d8, 6s2. This is the expected configuration. Here also, due to the increased nuclear charge, you may expect that both the electrons from the 6s orbital will be promoted to the 5d orbital. But that is not happening. Only one electron from the 6s orbital is promoted to the 5d orbital. Why only one electron is promoted from 6s orbital to the 5d orbital? Is because as we go down the group, the elements become more and more heavy. So in heavier elements, there is some relativistic effect. The relativistic effect makes the d orbital less stable and the s orbital more stable. And as we go down the group, the nuclear charge is more. So the nuclear charge is attracting the outermost electron inwards. But at the same time, the relativistic effect is not allowing both the electrons to be promoted to the 5d orbital. So the actual configuration is 4f14 and only one electron from 6s is promoted to 5d orbital. So 5d9, 6s1. So this is the electronic configuration of platinum. So in given options, you have to check. So the noble gas configuration in nickel is argon configuration, then for palladium, krypton, then for platinum, it is xenon. So in option A only, you are having core xenon configuration 4f14, 5d9, 6s1. So the option A is correct. The next question is the number of statements correct from the following for copper. The first statement is copper 2 complexes are always paramagnetic. So copper is having the electronic configuration 3d10 4s1. Copper in +1 oxidation state after the loss of one electron will have 3d10 configuration, and copper in +2 oxidation state after the loss of the next electron it will be having 3d9 configuration. So copper 2 is having 3d9 configuration. So in 3d9 configuration, how many unpaired electrons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So one unpaired electron is there. So it is paramagnetic only. So the statement 1 is correct. The next statement, copper 1 complexes are generally colorless. So copper in +1 oxidation state is having 3d10 configuration. So a metal ion, when it is having 3d10 configuration or 3d0, that is d0 configuration, it will be colorless in nature. So copper 1 complexes are colorless. This statement is also correct because it is having 3d10 configuration. Then going to the next statement, copper 1 is easily oxidized. So what is oxidized? It easily loses electron. So Cu plus 1 ion easily loses electron and it is converted to Cu2 plus ion. This statement is also correct because after the loss of the one electron, Cu2 plus ion is highly hydrated and it has a high hydration enthalpy. So this hydration enthalpy compensates the second ionization energy, that is the energy required to remove the next electron from this Cu plus 1 species. So it is having the highest hydration enthalpy and this hydration enthalpy helps to remove the next electron. So the Cu1 ion is easily oxidized. So the third statement is also correct. Then going to the last statement, in Fehling solution, the active reagent is Cu1. So this statement is wrong. In Fehling solution, the active reagent is copper tartrate. So in this copper tartrate, copper is present in +2 oxidation state. So Cu2 plus ions are only present. And how this copper 2 tartrate is produced? This complex is produced by adding the Fehling A solution with Fehling B solution. And this Fehling A solution is copper sulfate. And this Fehling B solution is potassium sodium tartrate with sodium hydroxide. So these two solutions mix together to give this copper 2 tartrate, and copper 1 species is not present. Cu2 plus ions are only present. So the number of correct statements are 3. The next question is, in 3D series, the metal having the highest M2 plus bar M standard electrode potential is. So in 3D series, we know that copper is the only element having positive electrode potential value. So copper is the element which is having the highest M2 plus bar M standard electrode potential. And what is the reason for this? Copper is having high enthalpy of atomization, and for the removal of 2 electrons from copper to form the Cu2 plus species, more amount of energy is required, that is high ionization energy is required. So the meaning is the simultaneous removal of 2 electrons from this copper atom to form Cu2 plus ion, high ionization energy is required. So this ionization energy is not compensated by the hydration energy because the hydration energy value is very low. It is having low hydration energy value and it is not helping for the removal of the 2 electrons simultaneously. So copper is having the highest M2 plus bar M standard electrode potential. Among the following, which is the strongest oxidizing agent? So let us see the electronic configuration. Manganese is having the electronic configuration 3d5 4s2. Mn3 plus is having the configuration 3d4. Then Fe iron is having the configuration 3d6 4s2. Fe3 plus is having the configuration 3d5. Then titanium is having the configuration 3d2 4s2. Titanium 3 plus is having the configuration 3d1. Then chromium is having the configuration 3d5 4s1. Then chromium 3 plus is having the configuration 3d3. So in this configuration, you have to check which configuration easily accepts electron, because here the condition mentioned is strong oxidizing agent. A strong oxidizing agent is itself reduced. So the species should be itself reduced. And what is reduction? It is gain of electron. So it easily accepts electron. So out of the configuration, Mn3 plus is having the configuration 3d4. So after the gain of one more electron, it will be converted to 3d5 configuration, and 3d5 configuration is more stable because it is half-filled configuration. So out of the given options, Mn3+ is the strong oxidizing agent, as it is having 3d4 configuration and it easily gains electron and become 3d5, and it is going to oxidize the other substance present in the reaction. The next question is, identify the element for which electronic configuration in +3 oxidation state is core organ configuration 3d5. So you have to check for which element present in +3 oxidation state the configuration is 3d5. So the given options are, the first option is ruthenium. Ruthenium is a 4d series element, so ruthenium is ruled out. Then going to manganese. Manganese is having the electronic configuration 3d5 4s2. Manganese in +3 oxidation state will have the electronic configuration 3d4. So it is not 3d5. So manganese option B is also ruled out. Going to option C, cobalt is having the electronic configuration 4 organ configuration 3d7 4s2. Then CO3+, after the removal of 3 electron, it will be having 3d6 configuration and it is not 3d5. So option C is also wrong. Then our correct option will be option D only. So iron is having the configuration 4 organ configuration 3d6 4s2. Then iron in +3 oxidation state, 2 electrons from 4s orbital is removed and 1 electron from 3d orbital is removed. So the configuration is 3d5. So our correct option is option D. The next question is the set having ions which are colored and paramagnetic both. So for a species to be colored, the species should not have D0 and D10 configuration. So the species should not have D0 and D10 configuration. Then we will see the options. Cu2+. Cu2+ is having 3d9 configuration in which 1 unpaired electron is there. Cr3+ is having 3d3 configuration. So 3 unpaired electrons are there. Then Se+ is having 3d1 4s1 configuration. 2 unpaired electrons are there. So all these species have unpaired electrons, so they are paramagnetic, and their configuration is also, it does not have D0 or D10 configuration. So our correct option is option A. Let us check the other options also. In option B, Cu2+ is again given, which is 3d9, but Zn2+ is given, which is having 3d10 configuration, so it will be colorless. So the option B is ruled out. Then going to option C, all the 3 species, Sc3+, B5+, then titanium in +4 oxidation state, all these elements have D0 configuration. They have 3d0 configuration, so they are colorless. So option C is also ruled out. Then going to option D, Ni2+ is having 3d8 configuration. So all the, then in Mn+7, it is having 3d0 configuration. So manganese is having the electronic configuration, core organ configuration 3d5 4s2. 7 valence electrons are there. In +7 oxidation state, all the 7 electrons are lost. So 3d0 configuration is there. And Hg2+ is also a group 12 element. It will be having 5d10 configuration. So the d0 and d10 configuration will be colorless. So option D is also ruled out. So the correct option is option A. The next question is, number of electrons that vanadium Z equal to 23 has in p orbitals is equal to. Vanadium atomic number 23 is having the electronic configuration, core organ configuration 3d3 4s2. So in the valence electron there is no p orbital involved, so you have to see this organ configuration. So that organ configuration is 1s2 2s2 2p6 3s2 3p6, then you are having 3d3 4s2. So the p orbitals involved are 2p orbital and 3p orbital having 6 electrons in each orbital. So the total number of electrons is 6 plus 6 equal to 12 electrons are there. So the answer is 12. The next question is the common positive oxidation states for an element with atomic number 24. The element present in atomic number 24 is chromium. So chromium has the oxidation states from +2 to +6, and the chromium does not exhibit +1 oxidation state. For chromium, there is no +1 oxidation state. For copper, which is having the configuration 3d10 4s1, there is +1 oxidation state, Cu+ exists with the 3d10 configuration. But for chromium, which is having the configuration 3d5 4s1, there is no +1 oxidation state. But rather than that, chromium is more stable in +3 oxidation state. In +3 oxidation state, it is having 3d3 configuration, which is half-filled T2G3 configuration. So it is more stable in +3 oxidation state when compared to +1 oxidation state. So the common positive oxidation states are in the range +2 to +6. So the correct option is option C. The next question is, in the ground state of atomic ion Z equal to 26, the spin only magnetic moment is dash into 10 power minus 1. So here you have to tell the spin only magnetic moment in terms of 10 power minus 1 bm. to find the spin only magnetic moment, the formula is nu is equal to n into n plus 2. So you have to find the number of unpaired electrons. The electronic configuration of iron is 3d6 4s2. 4s orbital is having 2 electrons, so the 2 electrons are paired. Then going to the d orbital, 6 electrons are present in 3d orbital. So 1, 2, 3, 4, 5, 6. So the number of unpaired electrons is 4. So n equal to 4. So you have to substitute that. So mu is equal to root of 4 into 4 plus 2 is 6. So root of 24, and the answer is 4.89 bm. But here they are not telling to round off to the nearest integer. First, you have to convert that in terms of 10 power minus 1. So for converting into 10 power minus 1, you have to multiply and divide this number by 10. So when you multiply by 10, it will come as it will come as, well, the decimal point will move. So 48.9. Then in the denominator you are having 110, you have to take that to the numerator. It will become 10 power minus 1 bm. Now you have to round off the answer. 48.9 we can write as 49 into 10 power minus 1 bm. So the answer is 49.